Section: Introduction. In this section, we explore the application of advanced generative models to decode images and text from brain activity, which has become a vibrant research area. We notice a competitive push in publications aimed at reducing reconstruction errors to create more accurate images and text. However, we argue that improving reconstruction quality does not necessarily mean we are enhancing our understanding of how the brain processes vision and language. There are several reasons why a method might yield better reconstructions while using the same or even less brain signal. For instance, a larger model might learn a stronger understanding of images and text, allowing it to produce better results with less information. Additionally, these models may become overly specialized to the types of images and text found in common datasets, which is concerning given the scarcity of open neuroscience datasets. We also face challenges in evaluating these reconstructions. Even well-intentioned modeling approaches can struggle with the limited evaluation methods available today. We emphasize the need to properly calibrate and recognize the limitations of these methods. To address the issue that improved decoding does not always correlate with a deeper understanding of brain function, we introduce a new metric called BrainBits. This metric assesses how reconstruction performance changes based on an information bottleneck. We establish linear connections from neural recordings to a smaller space, optimizing the reconstruction goals of each method. Our findings reveal that a bottleneck representing only a small fraction of the total brain data can still guide generative models to produce high-quality images. Specifically, we find that reducing the data to just 30 to 50 dimensions retains most of the reconstruction performance, depending on the evaluation metric. BrainBits allows us to separate the contributions of the generative model's prior knowledge from the actual brain signal when assessing models. This distinction is crucial for effectively using stimulus reconstruction to advance neuroscience. We advocate for reconstruction methods that genuinely reflect brain activity rather than relying solely on model priors. We propose three key components: creating a random baseline that does not use neural data, determining a method-specific ceiling for reconstruction, and evaluating performance based on bottleneck size. Ideally, models should achieve near-optimal performance only with larger bottlenecks, indicating they are truly utilizing neural signals. Models that show high baseline performance but only tap into minimal brain information are primarily benefiting from their prior knowledge. While our examples of BrainBits focus on fMRI data, this method can be applied to any type of neural recording. BrainBits also enhances interpretability by revealing which brain regions contribute to decoding based on bottleneck size, allowing us to probe the activity of these areas. Our contributions include the introduction of BrainBits, a novel method that clarifies how models utilize brain recordings for performance. In related work, we note that several recent studies have aimed to predict latent features from fMRI data to reconstruct stimuli. Techniques have been developed to project fMRI recordings to the bottleneck layers of pre-trained generative models, such as variational autoencoders and generative adversarial networks. With the success of models like DAL-E, more recent efforts have focused on mapping to the latent spaces of large diffusion models. Additionally, some approaches have utilized generative models for multimodal decoding of both images and captions. The growth of fMRI datasets, particularly the natural scenes dataset, which includes recordings from subjects viewing thousands of samples, has facilitated this research. This dataset is now a popular choice for many recent methods due to its size and potential for data-driven neural decoding. Various metrics for measuring reconstruction fidelity have been proposed, but none adequately consider the prior knowledge embedded in modern models. Section Summary. In this section, we discuss the limitations of current generative models in reconstructing brain responses, emphasizing that improved reconstruction quality does not necessarily correlate with better understanding of brain processing. We introduce BrainBits, a new metric that evaluates how reconstruction performance varies with information bottlenecks, revealing that high-fidelity reconstructions can often rely more on model priors than on actual neural signals, which is critical for advancing neuroscientific research. Section: Approach. In this section, we outline our approach to understanding how the quality of images reconstructed from brain data depends on the brain signals. We start with a reconstruction method that maps brain data to images and aim to analyze the impact of restricting information flow on the quality of these reconstructions. We achieve this by using a bottleneck mapping that compresses the brain data into a smaller vector. We define our images as a set where each image corresponds to a specific brain data response. Our goal is to determine the best possible reconstruction quality for a given restriction level, using a scoring metric to evaluate the quality. This allows us to create a curve that shows how reconstruction quality varies with different restrictions. We focus on linear transformations to find interpretable mappings that yield the best reconstruction quality. The performance of our model is assessed against randomly generated images and a theoretical maximum performance. To establish a baseline for random performance, we conduct bottleneck training using synthetic data generated from a standard normal distribution, which helps us understand the model's generative capabilities without brain input. For the maximum performance, we run the full reconstruction process using the actual latent representations instead of those predicted from brain data, allowing us to see the best possible reconstructions. We adapt three advanced methods, brain diffusers, Takagi and Nishimoto, and Tang et al., to compute what we call BrainBits. The first two methods focus on visual reconstruction, while the last one deals with language reconstruction. We compute BrainBits in conjunction with optimizing each method, meaning it is integrated into the process rather than being a simple additional step. This integration sometimes requires us to modify the optimizer, transitioning from standard regression tools to a deep learning framework. We optimize the reconstruction for various bottleneck sizes and evaluate the results using standard metrics, including a new metric called DreamSim, to demonstrate that BrainBits conveys consistent information across different metrics and reconstruction modalities. For brain diffusers, we utilize fMRI data from the natural scenes dataset, focusing on visual areas. We fit regressions to map the fMRI data to latent representations of images and captions. The predicted latent representation is used to create a rough version of the image, which is then refined using a versatile diffusion model. In the Takagi and Nishimoto approach, we also use the same dataset and mapping strategy but with some differences. We learn separate mappings for different brain regions, with one mapping focusing on early visual areas and another on a combination of various regions to predict text embeddings. These predictions guide the image generation process, and we implement two separate bottlenecks for the different mappings while keeping their sizes consistent. Section Summary. In this section, we outline our approach to assess how the quality of image reconstructions from brain data depends on the signal by implementing a bottleneck mapping that compresses the data. We adapt three state-of-the-art methods to compute BrainBits, integrating it into the optimization process to evaluate reconstruction quality across varying bottleneck sizes and different metrics, ensuring consistent performance regardless of the reconstruction modality. Section Tang et al. In this section, we demonstrate how our benchmark framework can be adapted to other modalities by exploring an fMRI to language reconstruction method. Initially, we fit an encoding model to connect GPT embeddings with brain activity. During inference, the decoder uses brain activity as input and employs GPT to suggest the next word based on the highest likelihood determined by the encoding model. We maintain the separation of training and decoding steps as in the original method. We introduce an information bottleneck by first creating a mapping from brain activity to a compressed vector, which is then linked to a GPT text embedding. Instead of using raw brain activity, we utilize these compressed representations and proceed with the rest of the process unchanged. This approach requires minimal adjustments and is the simplest adaptation for BrainBits. Tang et al. Reconstruct language from various sources, including perceived and imagined speech, and we report the average performance across these tasks, with more details available in the appendix. For our results, we apply standard metrics for image and text reconstruction. When calculating the CLIP score, we measure the absolute cosine similarity between images rather than averaging ranks, making our results comparable to CLIP score with a constant scaling factor. We also assess similarity using DreamSim. By including additional metrics, we show that the BrainBits message remains consistent across different measures. Models utilize only a small portion of neural recordings to achieve most of their performance. We incorporate information bottlenecks into 2 vision and 1 language reconstruction method, varying the bottleneck size while optimizing the original goals. After learning these mappings, we analyze the resulting reconstructions and the representations learned by the bottlenecks. We compute the effective dimensionality of these representations, the types of information they can decode, and how much weight each mapping assigns to different brain regions. We explore how much information is necessary to reconstruct images or text. Qualitative results are illustrated in one figure, while quantitative results are shown in another. For Brain Diffuser, a bottleneck size of 50 achieves 75%, 95%, 100%, and 89% of the original performance based on different metrics, starting from around 14,000 voxels. A similar trend is observed with the Takagi and Nishimoto method. Chance performance is notably high for both visual reconstruction methods due to strong data priors, but both methods also exhibit a surprisingly low ceiling in maximizing these metrics. For language reconstruction, the original method uses whole brain fMRI data, which consists of about 90,000 floating point numbers. A bottleneck size of 1,000 recovers 50% of the performance on average across subjects, as measured by BERT, and achieves 26% and 20% of the original performance based on Blue and Meteor, respectively. The word error rate is comparable. Chance performance is unexpectedly good, with specific scores varying slightly by subject. We also examine how effectively the bottlenecks are utilized. The bottleneck dimension sets an upper limit on the information extracted from the brain. For Brain Diffuser, a bottleneck of size 50 has an effective dimension of about 16, while the average effective dimension of the fMRI inputs is 2,257. Language models show a smaller effective dimension, with a bottleneck of size 1,000 having an effective dimensionality between 5 and 20, depending on the subject. We analyze which brain regions are most significant by plotting the weights of the bottleneck mapping for Brain Diffuser. Most weight is concentrated in the early visual cortex's peripheral voxels. As we increase the bottleneck size, the model continues to prioritize these areas rather than expanding to new ones. Ideally, we would want models to broaden the brain regions they effectively utilize as the bottleneck size grows. Lastly, we investigate what information the bottlenecks contain by decoding visual features from various bottleneck sizes for Brain Diffuser. We find that lower-level features like contrast and brightness are quickly accessible at small bottleneck sizes but are also rapidly exhausted. In contrast, higher-level features, such as object class, may become more influential as the bottleneck size increases. Section Summary. In this section, we extend our benchmark framework to fMRI to language reconstruction by implementing an information bottleneck that compresses brain activity into a vector mapped to GPT embeddings, allowing us to analyze the effectiveness of different bottleneck sizes on reconstruction performance. Our results indicate that a significantly reduced bottleneck can still capture essential information for reconstructing images and language, while revealing insights into the effective dimensionality of the representations and the brain regions most influential in the process. Section: Limitations. In this section, we discuss the limitations of BrainBits. We need to rerun the decoding process multiple times, which can be costly depending on the method we choose. Additionally, BrainBits is not a straightforward plug-and-play solution. It requires joint optimization with the reconstruction method. While we can use a simple fixed compression method like PCA for a rough estimate, optimizing both the bottleneck and the reconstruction method can be complex and may need manual adjustments. BrainBits can be integrated at various stages of a method that extracts information from the brain, which complicates its use as a simple library call. Instead, we must adapt our models to compute BrainBits, although this adaptation is usually straightforward. The resolution of BrainBits is influenced by the size of the bottleneck and how we compute it. We focus on a linear bottleneck to avoid complicating the model with additional computations. In the future, We plan to explore vector quantization methods, which may perform better for smaller bottlenecks, although small bottlenecks might not be very useful since our goal is to explain more of the brain's activity. Moreover, current metrics for images and text are limited, making it challenging to assess reconstruction performance. This issue is exacerbated when random performance is high due to strong model priors, especially when these priors enable good performance with minimal brain information. Understanding these factors is essential for evaluating our absolute performance and explaining brain representations. Regarding computational requirements, we generated all mappings and images using 2 NVIDIA Titan RTXs over the course of a week. Our code is available for further exploration.